All right, so let's go over some vocab. We were talking about confidence intervals. We did a little activity about IQs of seniors at our school, and we created this confidence interval. So the percent confidence interval, a 95% confidence interval gives an interval of plausible values for a parameter. Not guaranteed, but plausible values. There's still a chance that it might be outside this interval of values. And it's calculated by taking your point estimate plus or minus your margin error. Actually, your point estimate is a statistic. It's your statistic plus or minus. We're going to learn that we have this crit value. This, was two standard deviations, but we're going to call it a crit value times the standard deviation of your statistic, the standard deviation of your stat. So we're going to learn that this is actually how you calculate a confidence interval, all confidence intervals. But these two things combined give us our margin of error. It gives us the number that we add and subtract to our stat to get our interval. The difference between the point estimate and the true value of the parameter will be less than the margin of error in 95% of all samples. Kind of a definition of margin of error, I guess. And the confidence level gives the overall success rate of the method for calculating the confidence interval. That is, 95% of all possible samples. In 95% of all possible samples, the method would yield an interval that captures the true parameter. Perfect. Interpreting confidence intervals. Put a star by this one. We're going to be doing this a lot. To interpret your interval, we simply state something along these lines. We are 95% confident that the interval from blah to blah captures the parameter in context, the true mean IQ of JCS seniors, something like that. So let's use it as let's actually interpret this interval here. So we are 95% confident that the interval from 104.2 to 114.2 captures the true population mean IQ of JCS seniors. Sorry, I'm sloppy. Okay. Make sure we get our interval in there. Make sure we get the parameter we're talking about. Make sure it's clear that it's a population. And then let's make sure we get context. That's kind of the three pieces that they're looking for. Common mistake. So we talked about this quite a bit in class. I want to talk about it here, but maybe not as much. It is incorrect to say this. The probability that the population mean is in the interval is 95%. Why? So let me give you two statements. One that is true. So this is a false one. The probability that the population mean is in our interval is 95%. This would be a correct way of saying it. The probability that our interval captures the true mean is 95%. So if you kind of think those two sound very similar, you're right, but there's a subtle difference between them. And it has to do with this idea of probability. In order for us to have probability, to discuss probability at all, we have to have a random event. Okay? If we create an interval, and our interval is, let's say, 105 was our number, so 104 to 109. This is our interval. And we want to talk about the probability that the true mean is in this interval. Well, the issue is that the true mean doesn't depend upon random chance. It's 105. It is set in stone. It's not changing. So either it's in the interval or it's not in the interval. There's really no chance event happening there. So it's incorrect to say so right now the probability is 1. it's guaranteed to be in there. And if my interval would have been 106 to 112, the probability would have been 0. Just because you don't know what the probability is, or you don't know what this is, doesn't really change the fact that there isn't that there's not really a probability there. So what is the random chance event? The random chance event is actually our interval. Every time we take a new sample, we get a new interval in a different location. The probability is in the fact that our interval is going to be created at the right spot in order to capture the true mean. So the correct way to say it is, there's a 95% probability that our interval is going to be located in a position that will capture the true mean. It's a subtle difference. I wouldn't worry too much about it. I would just encourage you to avoid the word probability altogether, but word your conclusions like this. We are 95%, oh my gosh, I forgot the most key word, confident. We are 95% confident. Yeah, you got it. You want to make sure you get the word confident in there. Don't use the word probability, but talk about we're confident that our interval captures the mean rather than the mean being in my interval. It's a subtle difference, but one that's nice to understand, I guess. Okay. Interpreting confidence levels. This is less common, but it usually shows up on my tests. This is a harder one to interpret. I mean, we're going to do these all the time, but this is a little bit less common. What does it mean to be 95% confident? Well, being 95% confident means that if we take many samples of the same size from the population, about 95 of them will result in an interval that captures the actual parameter. So if I construct an interval, I get a mean, I get an estimate, and then I get an interval, and I captured. I get another mean, I get another interval, and I captured. I get another mean, I get another interval, and I captured. But every once in a while, you're going to get one that doesn't capture. 95% confident means if you do this many, many times, hundreds of times, thousands of times, millions of times, 95% of them will capture and 5% of them will miss. That's what 95% confident means. Explore the confidence intervals applet. Okay, so this is maybe going to be the last thing we do in the video. It's just really an illustration of exactly what we've talked about several times here now. But it's a nice visual if you want to play around with it. So this is for, I guess it doesn't even really say what, I guess we're talking about means here because this is a mean. So this is this is black curve is my population distribution. The red curve is my sampling distribution. So if I take, and then we're taking samples of size 20, confidence intervals of 95%. If I take one sample, these dots represent the numbers in my sample. You can see that it came from the population. But if you take the average of those, it gives you a dot right there. That's my X bar. That's a value from this red sampling distribution. And then we're constructing a 95% confidence interval. So we captured. Let's do another one, and another one, and another one. Looks like we're capturing every single time. But you do it enough, ooh, almost missed there, but you do it enough, and eventually you're going to miss, okay? So the question is, what percentage of the time are we going to miss? Well, so far we've missed 1 out of 16 for 94%. Well, let's do this a bunch of times. There's 25. That last 25 I didn't miss any. This one I'm missing 5. Missing 1. Missing none. Missing 2. Missing 1. You do it hundreds and hundreds and hundreds of times, and you can see your capture rate on average looks like it's about 94%, close to the advertised 95%. Okay? So what's going to happen if I, let's do one where we have like maybe 1 or 2 misses. Here's 2 misses. So what happens if I, and you can click on these things and see what the sample is. And why did we miss here? Well, we just got a really small sample that had a lot of small values. So what happens if I change my confidence level? What happens if I lower my confidence level? Well, if you lower your confidence level, you can see these intervals are are, oh gosh, that's a bad example. Let me do another one. If I lower this confidence interval, you can see that you can see that your intervals are narrowed and you miss more. Like when you're at 95%, we only had one miss. But as I lower it to 92, 93, 90, I got 3 misses. 85, I got 4 misses. Go down to 80, I guess I'm still at 4 misses. Yeah, 4 misses. So, and these are all the same samples. So what happens is if you're less confident, you have a more narrow interval because you're willing to risk missing the true value more. Now, if you want to be more than 95% confident, we have one miss. If I make it bigger, it's going to widen those intervals. And as you can see, that miss is eventually going to widen out to a capture if you're running it like 90. So let's do 99%. Let's reset. Now if I sample, all hits. These intervals are wider. All hits, all hits, all hits. There's a miss. You do this many, 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 many times, we should capture about 99%. You can see it's 99%. Okay? All right, so what if we change the sample size? What if we sample more? By the way, you can see what happens to your red sampling distribution is if your sample size goes down, it widens that sampling distribution out. More variability. If you make it bigger, it makes it more narrow. I think it also probably changes the scale a little bit, but so let's say instead of 20 sample size, let's go up to 50. So what's going to change? Well, what changes is you can see the interval is much more narrow because the sampling distribution is more narrow. And because you have a larger sample size, your interval is going to be much narrower. You're going to get better estimates. But what percentage are we going to miss if we increase our sample size? Sometimes people say if we increase our sample size, we're going to miss less. Well, no, because we're still working at 95% confidence. So it made them narrow. We should still miss 95% of the time. Many, many times. We're at 97%. High. 96. I'll keep going, and it's going to kind of settle in law of large numbers onto 95% about maybe. Well, we might stay at 96 for a while. Okay, and again, you can lower your confidence level and make them even more narrow. You can raise your confidence level, make them wider, and capture more often. So I guess I want you to see that the sample size and the confidence level work independently of each other. Doesn't matter what your sample size is. Your confidence level will still capture the right percentage of the time because it takes both into account. Kick this up to 200. 250 is the largest I can go. So when we take our samples, look at how narrow these intervals are. Very, very narrow. When we give estimates, we can say the IQ is somewhere between 103 and 104.5 because we have such a large sample size, even at 95%. Now, if you want to even make it even lower level confidence level, it's going to make them even more narrow. But even if you kick it up to 99%, they're still pretty narrow. But now we're going to capture 99% of the time. So sample size and confidence level work independently of each other, and the thing that helps that accounts for it, and we'll talk about this here in a little bit, is this formula, right? The crit value is dependent upon the confidence level, and the standard deviation is dependent upon your sample size. So those are going to work together to give you this margin of error of varying widths. All right, we're at 14 minutes. We got one more video to finish this up, and we get a Garfield comic at the end. Sweet.